Hey everybody, Chris McClure here. We are now going to have a discussion on complex numbers so that now we can talk about how every quadratic equation really has at least one solution. So in the case of there being a negative discriminant, well, we can now start thinking about taking square roots of negative numbers so that we actually have solutions. Now, you may have seen this critter before. It's called I, and we call it the imaginary unit. It's our imaginary friend. And it's that number whose square is equal to negative 1. Now, just as an aside, if you were to go on to take an electrical engineering sort of class, for those of you who are thinking about going into EE, well, they don't use I. Typically, they'll use a J instead of I, because I is also used as the symbol to indicate current flow. Anyway, but for us in this class, we're going to use I as that imaginary unit whose square is equal to negative 1. All right. Now, when we take some real number together, add it to some multiple of I, as in the form of A plus BI, then what we have done is formed a complex number where A and B are both real numbers. So, for example, 2 plus 3I is a complex number, where the 2 is said to be the real part, and the 3 would be the imaginary part. It's the number that you multiply by I, which is the imaginary part. So 3, the real number 3 is the imaginary part of the complex number. So the imaginary part of the complex number is actually a real number. Okay, and of course the 2 in this case is the real part. Alright, so just like any numbers, you can add them, subtract them, multiply, divide, take square roots and powers, and everything that you could do with real numbers, you could also do with complex numbers. Because, by the way, the real numbers forms a subset of the complex numbers. Alright, so if you are comfortable using set notation, if you were to say that this capital R represents the set of real numbers, and we know what we mean by real numbers, all the rationals and the irrational numbers and so forth. And if this C right here is the set of complex numbers, then the set of real numbers is a subset of the complex numbers. And we can just demonstrate that by simply saying that you take any real number, like R. So let R be an element of the set of real numbers. Then we could write R as R plus 0I, which is a complex number. But not all complex numbers are real numbers. For example, 2 plus 3I is a complex number, but not a real number. In order for the complex number to be a real number, the imaginary part would have to be 0. Okay? Alright, let's move on here. Alright, so how do we know that two complex numbers are equal? Well, it should be self-evident, of course. Just like, two numbers are equal if and only if they have the same value, right? Well, complex numbers will be equal if and only if their real parts are the same and the imaginary parts are the same. So if I were solving some weird equation like x plus 3 plus 3i is equal to maybe 6 plus quantity y minus 2i. Well, I could solve this equation by noting that the real part x plus 3 must be equal to 6. So that would imply that x is equal to 3. And also that the imaginary parts would be the same. So we would have 3 is equal to y minus 2, which would imply then that y is equal to 5. Okay? So two complex numbers are equal when their real parts are the same and their imaginary parts are the same. We can add two complex numbers together by adding their real parts together and adding their imaginary parts together. So a plus bi plus c plus di is equal to a plus c plus b plus di. And also, of course, we could take the difference of complex numbers, meaning we can take one complex number minus another complex number. And just like we did with the sum, we just take the difference of the real parts and the difference of the imaginary parts, okay, to get a new complex number. So let's just do a couple of examples here. Let's suppose that we're going to add 3 minus 2i plus 5 minus 4i. 3 plus 5 is 8. 3 plus 5 is 8, and then the negative 2 plus negative 4 will give you negative 6. So we'll have the 8 minus 6i, which is the same thing as 8 plus negative 6i. Same thing, but if you have 8 plus negative 6i, it's more conventional for us to write and say 8 minus 6i. Okay. If you have 3 minus 2i minus 5 minus 4i, then you can carry out this difference by taking the difference of the real part, 3 minus 5, which is going to be negative 2. 3 minus 5 is negative 2. And then negative 2 minus negative 4, which is negative 2 plus 4, which is positive 2. So we have negative 2 plus 2i is the result of the difference of those two complex numbers. Okay, moving on here. We could also multiply two complex numbers together, and we would carry it out by doing a foiling sort of action. We could take the 3 times the 5, which is 15, and plus 3 times negative 4i. Alright, so we have the 3 times 5, which is 15, plus 3 times negative 4i, plus negative 2i times 5, plus negative 2i times negative 4i, what you see there. Go through and simplify from left to right. 3 times 5 is 15. 3 times negative 4i is going to be negative 12i. Negative 2i times 5 is negative 10i. And negative 2i times negative 4i. Now, here's the thing. Negative 2 times negative 4 is positive 8. You know, you have I times I, which is I squared. Okay? But, by the way, what is I squared? It's negative 1. So, replace the I squared by negative 1. And then you have 15 minus 8, which is negative 7. Excuse me, positive 7. 15 minus 8 is positive 7 minus 22i. So 7 minus 22i would be the result of taking 3 minus 2i times 5 minus 4i. So the result of the product of two complex numbers is going to be some other complex number. Now, before we go any further, let me just point out that if you happen to have a graphing calculator like a TI-84, you could probably carry out your arithmetic with your complex numbers on your graphing calculator. Let me show you how to do it. Now, if you go into the mode menu and you go down to your number setting using your down arrow button, and then right arrow over to where it says A plus BI, that means that the numbers are going to be expressed as real numbers. So then we can then enter a real number as in 3 plus 2i, like that, where the I is located right here with the bottom key, but you have to hit the second button in order to access that number. So 3 plus 2i. And then you can add that to some other real number like 5 minus 2i. Now what we did is we added 5 and then we subtracted 2i. If we actually wanted to add 5 minus 2i, you just have to be careful. Let's just hit add and then in parentheses 5 minus 2i. Okay. Anyway, you can also subtract just like we added. We could also multiply. So let's multiply that. Make sure that you do that you put the second complex number in parentheses. So suppose it's 9 minus a half times I, for example. And there's the result. You could even raise your complex numbers to powers. Like so, for example, we can square that previous complex number to give you a new complex number. We can even take cube roots, so we could raise that to the 1/3 power, which means taking the cube root, the result of which is a kind of a messy looking complex number, but indeed it is a complex number. Notice the I at the very end of the number. Okay? So that's how you can do arithmetic and calculations involving the complex numbers on the calculator. Alright, so we just talked about how to carry out the product of the complex numbers. It really comes down to, instead of memorizing the formula, just FOIL out that product as you would as the product of two binomial polynomials. Okay. Now let's talk about conjugate, which is interesting. Now when we were dealing with binomials, for example 3 plus 2x, I think that I talked about the conjugate of this by replacing the plus operation in the middle by the minus. So the conjugate of 3 plus 2x is 3 minus 2x. The conjugate of 3 minus 2x is 3 plus 2x. Well, we have the same concept with complex numbers. If you have the complex number z is equal to a plus bi, then the conjugate of that complex number is going to be a minus bi. Now, let me just do it as an aside here and mention that z is often used as the generic number that is complex. Just like we oftentimes will use x as our generic variable or generic real number. Well, z plays that same role but for complex numbers. So when you use z in the complex sense, that just means some complex number. And we oftentimes will use a as our real part and b as our imaginary part. So anyway, then here's the notation for the conjugate of complex number z. you just have z with the little bar over the top. And if you have a plus bi and you have the bar over the top, that means taking the conjugate of it. Okay? So if you have 2 minus 3i and you want to take the conjugate of that number, that's going to be 2 plus 3i. For example, so let me erase all this ink. Oops. So what happens, do you think, if we were to take some complex number and multiply that number by its conjugate? So for example, 3 minus 2i, do you remember the conjugate of 3 minus 2i? 3 plus 2i. Alright? And now let's multiply those numbers together and see what happens. So z times z bar means the complex number z times its conjugate, 3 minus 2i times 3 plus 2i. Now remember, as in multiplying a binomial times its conjugate, you end up with the difference of squares. Well, we'll have that same issue here. 3 times 3 is 9 minus quantity 2i squared. But what is I squared? Negative 1. So you have negative 4 times negative 1 is 4. So 9 plus 4 is 13. So that's what's going on here. We have the 9, which is the 3 squared. Of course, the middle terms cancel. And we have negative 4i squared. I squared is negative 1. So you have 9 plus 4, which is 13. So the result of taking a complex number times its conjugate is always going to be a real number. Okay? So if you have complex number a plus bi, then the result of taking z times z bar is equal to a squared plus b squared. Always a real number, which is going to be useful then, because there's going to be some times when we have some quotient of complex numbers, and we are oftentimes are not going to want to see a complex number in the denominator, because when we carry out division of complex numbers, we want the result to be in the form of a plus bi, where a is a real number and b is a real number. We don't want to see it in this form, like you see there, where 1 is, hey, it is a complex number. Okay? So how can we get rid of this complex number in the denominator? What can we multiply this fraction by? What version of 1 can we multiply the 1 over 3 minus 2i by in order to get a real number in the denominator? Oh, it really comes down to multiplying by the reciprocal, or by the conjugate, 3 plus 2i. So the reciprocal of 3 minus 2i is 3 plus 2i. So multiply by 3 plus 2i over 3 plus 2i. And on the numerator, you'll have, for this example, 3 plus 2i. In the denominator, you'll have 9 plus 4, which is 13. So 3 over 13 plus 2 over 13i would be the result of taking 1 over 3 minus 2i, which, by the way, means that we have found the reciprocal of the complex number 3 minus 2i, which means the multiplicative inverse. And I guarantee that if I were to take 1 over 3 minus 2i times this new number that we found, the result would be equal to 1. Okay? Alright, let's do another example here. We're doing this division, 3 minus 2i divided by 5 minus 4i. So using that same idea that we saw in the previous slide, let's multiply the numerator and denominator by the reciprocal of 5 minus 4i, which will be 5 plus 4i. So we multiply those two numerators out, 3 minus 2i times 5 plus 4i, and that works out to be, when we FOIL it out, we got 15, which is 3 times 5, plus 3 times 4i, which is 12i, plus negative 2i times 5, which is negative 10i, plus negative 2i times 4i. Now, negative 2 times 4 is negative 8 times the I squared, which is going to be negative 1. So this last piece will be positive 8, which you'll combine with the 15. In the denominator, we have 5 squared plus 4 squared, which is 25 plus 16. That'll be 41. So going through and simplifying, in the numerator, we have 15 plus 8 is 23. And then the 12i minus 10i, which is 2i. So the numerator is 23 plus 2i divided by 41, which then you could write as 23 over 41 plus 2 over 41i. In the homework, when you do these various calculations involving complex number, they want you to write the answer in the form of a plus bi, so you have to make sure that you do the division correctly, and then make sure that when you see your your complex number in this form, that you break it up into 2 separate fractions for your real and complex parts. Alright, so if we have z is equal to 3 minus I, and w, which is another popular generic variable for a complex number, and you have w equals 2 minus 5i, what is z divided by w? That'd be 3 minus I over 2 minus 5i. So now we know what to do to simplify this fraction. Just multiply the numerator and denominator by the conjugate of the denominator, which is 2 plus 5i. And then you'll FOIL out the numerator, 3 minus I times 2 plus 5i, and you know what to do there now. In the denominator, you have 2 squared plus 5 squared, which is going to be 29. So on the numerator, that, you'll have 6 plus 5, which is 11, and then 15 minus 2, which is 13. Denominator is 29. So the resulting complex number is 11/29 plus 13/29 I. Part B, you have z plus w. Now, what do you suppose that you'll do first, according to what they're asking for here? Do we take the conjugate first, or take the sum of z plus w? And the answer is take z plus w first. Now, z, remember, is 3 minus I. W is 2 minus 5i. So add those two complex numbers together. 3 plus 2 is 5. Negative I minus 5i is negative 6i. And then take the conjugate, which will give us 5 plus 6i. Part C, here we're taking a complex number plus its conjugate. Z plus z bar. So what do you suppose happens when we take a plus bi plus a minus bi? You see that the imaginary parts will cancel each other out, leaving you just with 2a, meaning 2 times the real parts. That'll be 3 plus 3, which is 6, because the i's will cancel. Okay? Moving along here. If you had a complex number with the imaginary part being 0, then you just have a real number. And the conjugate of a real number, a, you can write a as a plus 0i. That would be a minus 0i, but hey, you still have a. So if you have real number a, it's still technically a complex number. But like all complex numbers, you can take the conjugate of it. But the conjugate of a real number is just the real number itself. Also, if you were to take the conjugate of a real number, it's just the real number, or of the complex number. The result is the complex number. And you can see that just by saying, okay, we have a plus bi, that we have the conjugate of a plus bi is a minus bi. But then the conjugate of a plus bi is the conjugate of a minus bi, which is a plus bi. Okay, so that proves the z bar bar is equal to z. Also, z plus w conjugate is the same as the sum of the individual conjugates. So the conjugate of the sum of two complex numbers is the sum of the conjugates. That should be easy to prove. A plus bi is one complex number, plus c plus di is another complex number, and we're taking the conjugate of that sum. But a plus bi plus c plus di, just add the real parts. You have a plus c plus b plus di. And you're taking the conjugate of that, and you'll have a plus c minus c, b plus di. But then unpackage this, you'll have what, a minus bi, and then plus c minus di. But a minus bi is the conjugate of the a plus bi, and c minus di is the conjugate of the w. Okay? All right, so moving along here. Also, it turns out that the conjugate of the product of two complex numbers is the product of the conjugate. So look, if you need to form the product of two complex numbers and also take the conjugate, well, it doesn't matter what order you do it. You can take the conjugate first and then the product, or vice versa. Let's also talk about powers of the real numbers. We know what real number powers are, like 3 squared is equal to 3 times 3, which is 9, and 3 to the third power is 3 times 3 times 3, which is 3 times 3 is 9 times 3 is 27. Well, same idea with the imaginary unit, I. We know that I is that number such that I squared is equal to -1. So it shouldn't be a surprise that I squared is equal to -1. And oh, by the way, I to the 1 power is just I. But what's I cubed? Well, I cubed is I squared times I, but I squared is -1. So I cubed is -I. Now, I to the 4th power is I squared times I squared. But I squared is -1. So you have -1 times -1, which is 1. I to the 5th power is I to the 4th times 1. But I to the 4th is 1. So you have I. I to the 6th power is I to the 4th times I squared. I to the 4th is 1. So you have I squared, which is -1. I to the 7th power is I to the 4th times I cubed, but I to the 4th is 1, and I cubed is -I. So the result is -I. I to the 8th power is I to the 4th times I to the 4th, which is 1 times 1, which is 1. And in fact, if you have I raised to any positive integer power, like, for example, I don't know, 50, then to evaluate this, all you need to do is to take a look at that exponent and then subtract off the nearest power of, or not power, but multiple of 4 that's less than that exponent. So for 50, the nearest multiple of 4 that's less than it is 48. So you could write I to the 50th power as I to the 48th times I squared. And of course, 48 plus 2 is 50. But then I to the 48th power is I to the 4th times 12, and then times I squared. But I to the 4th is 1, 1 to the 12th power is 1, so we're just talking about I squared, which is negative 1. So I to the 50th power is negative 1. So that's kind of gives you a technique of evaluating high powers of I. What is I to the 33rd power? Well, again, what is the nearest multiple of 4? That's less than 33. The answer is 32. So I to the 32 power is 1 times I, which is I. Okay? You have I to the 82 power. What is the nearest multiple of 4? That's less than 82. And the answer is 80. And I to the 80th power is just 1 times I squared, which is negative 1. Okay? All right, moving along. We could take a complex number raised to any power or any root. Like 3 minus 2i, we could raise that to the 3rd power. And, namely, we can FOIL it out like we would use in a binomial, but we could also use formulas from our binomials to quickly write our powers. We know that the 3rd power of a binomial, x plus a cubed, could be written as x cubed plus 3ax squared plus 3a squared x plus a cubed. Well, hey, 3 is going to take the place of x, and negative 2i is going to take the place of a. So then we can go ahead and use this formula, replacing x by 3 and replacing a by negative 2i. So that's what we've done here. Here's your x cubed plus 3ax squared okay, plus 3a squared x, and then plus a cubed. And then simplify. Now let's tackle these powers of I. I squared is negative 1, so you have negative 36i there. I cubed is negative I, so you have 8i there at the end there. So combine like terms, and you end up with negative 9 minus 46i as the result of taking 3 minus 2i cubed. Any power of a complex number is going to be a complex number. Any root of a complex number is going to be a complex number. Probably the most interest that we have in complex numbers is in solving the quadratic equations where the discriminant is negative. Now let's just remind ourselves that when we are taking the square root of a negative number, like square root of negative n, where n is some real number, well, the square root of negative n means the square root of negative 1 times n. Now, you have square root of negative 1 times square root of n. But square root of negative 1 is I. And then, of course, with the square root of n, you'll simplify that. Like, for example, if n is equal to 8, then you could pull out a 4 from under the square root side, which becomes 2 on the outside. So 2 root 2, I. So what is the square root of negative 1? It's I. What's the square root of negative 9? Well, you could write negative 9 as negative 1 times 9, but square root of negative 1 is I, square root of 9 is 3. So the result is 3I. Square root of negative 18. Now, square root of the negative 1 is automatically I, so you can pull out the I, the square root of negative 1. That negative 1 becomes I on the outside. And then you have square root of 18, which you can simplify as square root of 9 times square root of 2. Square root of 9 is 3. So the result is 3 root 2 times I. That's what the square root of negative 18 is. 3 root 2 I. So if we want to solve the equation x squared equals 9, that's no problem. We could say that's x equals plus or minus 3, huh? But what about x squared plus 25 equals 0? That's going to be x squared is equal to negative 25, huh? So that means that x is equal to plus or minus 5i. Okay? So that's what we're saying there. Because, taking square roots of both sides, square root of negative 25 is 5i, so you have plus or minus 5i. And then here again is our quadratic formula that now is going to always produce at least one solution. Now, if the discriminant b squared minus 4ac is negative, the result is going to be complex numbers. In fact, a complex conjugate pair of solutions. If b squared minus 4ac is 0, then you'll just have one unique solution, negative b over 2a. And of course, if b squared minus 4ac is positive, then you'll have two real unique solutions. So let's do a couple of examples here. First, we have x squared minus 6x plus 13. Let's go ahead and solve this quadratic equation by plugging in 1 for a, plugging in negative 6 for b, and plugging in 13 for c into the quadratic formula. And when we evaluate the discriminant for b equals negative 6 squared, which is 36, minus 4ac, well, 4ac is 52, so 36 minus 52 is negative 16. We have a negative discriminant. That means that we're going to have complex solutions. Then the square root of negative 16 is 4i. Yeah. So our quadratic formula says that we have x is equal to negative b. b is negative 6, so negative 6 is 6, plus or minus the square root of negative 16, which is 4i. So we have 6 plus or minus 4i over 2 times 1, which is 2. All right, so let's simplify all that. 6 plus or minus 4i over 2. You can cancel 2's, and leaving us with 3 plus or minus 2i. So you have two solutions, 3 plus 2i and 3 minus 2i. Now, we could write the solution set as 3 plus 2i, comma, 3 minus 2i. So this just repeats what we just talked about. The sign of the discriminant indicates the nature of our solutions. Let you look at that. So here's a couple more examples. We're not going to actually solve the equation. We just want to know what is the nature of the solution. So we just evaluate the discriminant. For part A, b squared minus 4ac is what? 3 squared minus 4 times 2 times 1. 9 minus 8 is 1. The discriminant is positive. That means that we will have two unique real numbers. Now for part B, evaluate the discriminant. B squared minus 4ac is negative 2 squared minus 4 times 5 times 4, which is going to give us negative 76. Which is a negative number, of course, and that means our discriminant's negative, which means that we'll have a complex conjugate pair. of solutions. And then for part C, the discriminant works out to be 0, which means that we'll have one unique solution to our complex, or to our quadratic equation. One unique solution, same thing as saying that the quadratic polynomial has one double root. Okay, so that's it. That's the down and dirty discussion of complex numbers. We have more things to talk about in the complex world, but we're not going to spend a whole lot of time with complex numbers in this course. If you're interested, then we'll have more of a discussion in a trigonometry class sometime. Okay? Take care, and I'll see you in the next lecture, where we are going to be taking a look at equations involving radicals, meaning square roots, cube roots, etc. Okay, have a good day. I'll see you next time.